Today we're going to talk about how we find the zeros of polynomial functions, or to put it another way, how we solve polynomial functions and get the roots for them. The first tool we will talk about is the rational zero theorem, or sometimes referred to as the rational root theorem. This is a theorem that gives all possible rational roots of a polynomial equation. Now, not every number in the list will be a zero or root of the function, but every rational zero or root of the polynomial function will appear somewhere in the list. So let's discuss this by using a particular example. So let's say we want to list all possible rational zeros of f of x is equal to minus x to the fourth plus 3x squared plus 4. All right, now, all we're initially going to be concerned with are two things. We're going to be concerned with the constant term, and we're going to be concerned with the leading coefficient. So the leading coefficient is minus 1, and the constant term is 4. So what we want to do is consider all the factors for each of these. So if we're talking about 4, the only way you can get 4 is either 4 times 1 or 2 times 2. And obviously we could have minus 2 times minus 2. So all possible factors for 4 are going to be plus and minus 1, plus and minus 2, and plus and minus 4. Similarly, if we look at the leading coefficient, all possible factors there, it's fairly simple. It's either plus or minus 1. So the possible rational zeros are simply equal to the factors of the constant term divided by the factors of the leading coefficient. So each factor of the constant term you have to divide by each factor of the leading coefficient, and that'll give you your list of possible rational zeros. So in our example here, the possible rational zeros will simply be plus and minus 1, there we go, plus and minus 1, plus and minus 2, and plus and minus 4. So a fairly short list, but partly because the leading coefficient is only minus 1, so we're just dividing by 1, so we simply get the same factors as what we had for the constant term. So what the rational zero theorem is saying is that all rational zeros or all rational roots for this particular polynomial are included in this list. Now this does not mean that plus minus 1, plus minus 2, plus minus 4 are all roots. It just means that the actual roots are included in this list. Okay, now we'd like to see how we can use the rational zero theorem to actually find the zeros of a polynomial function. All right, so again, I'm going to take and use another example. So my example will be, the function will be f of x is equal to x cubed plus 2x squared minus 5x minus 6. And we want to find all the zeros. All right, so we start off by looking at the leading coefficient, which again, we can see here is 1. So therefore, the factors of that leading coefficient are simply going to be plus or minus 1. And then we look at the constant term, which in this case is minus 6. And the factors of that are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now, in order to get the list of all possible rational zeros, we divide the factors of the constant term by the factors of the leading coefficient, and we're simply, since the leading coefficient is 1, we just repeat what we had for the constant term. So the possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. All right, so now we want to go and determine which of these possible roots are actual roots. So let's start by saying possibly 1, okay? So we're going to start with 1, and we're going to use synthetic division. So we're going to stick 1 in the box here. Now we're going to look at the coefficients of the function, which are 1, 2, minus 5, and minus 6. And we're going to use synthetic division and see what we get. If we get a remainder of 0, we know that this is one of the zeros of the function. So we start off, bring down the 1, multiply by 1, we get 1, add, we get 3. 1 times 3 is 3, minus 5 plus 3 is minus 2. Minus 2 times 1 is minus 2, and we end up with minus 8 for a remainder. Well, since we've got a remainder, we know that 1 is not a 0 for this function. All right, so let's try 2. So we'll put 2 in the box and see what happens. Same coefficients, 1, 2, minus 5, and minus 6. Using synthetic division, we bring down the 1, multiply by 2. 2 plus 2 is 4. 4 times 2 is 8. Minus 5 plus 8 is plus 3. 3 times 2 is 6. Minus 6 plus 6 is 0, so there's a 0 remainder. So therefore I know that x equals 2 is one of the zeros of this function. Well, let's see if we can figure out what the others are. We've got a third degree, so therefore we have no more than 3 roots. So we've got 1. Now let's use the coefficients we just got for the result of the synthetic division. That's 1, 4, and 3. So that means, what do we have now? We've got x squared plus 4x plus 3 equals 0. And we should be able to factor this. This looks easy enough to factor. So we got x, and we got x again, equals 0. Both signs are plus, so both signs down here have to be plus. The only factors for 3 are 3 and 1. So therefore my other 2 zeros for this are x equals minus 3 and x equals minus 1. So now we have all 3 zeros or roots of this polynomial. And we use the rational zero theorem to take and come up with 1, and which brought us down to a quadratic, which we could factor to get the other 2. Up until now, we've worked with polynomial functions and attempted to find the zeros or roots of them. Now we're going to attempt to find a polynomial function when we are given the zeros or roots. We're going to do this by using something referred to as the linear factorization theorem. We know that for any polynomial, f of x, we can write it as a to the n, where that a to the n is a constant, times each of the factors of that polynomial. So where c1, c2, all the way out to cn are zeros, we can write it as f of x is equal to a to the n, parentheses, x minus c to the 1, parentheses, parentheses, x minus c to the 2, parentheses, all the way out to x minus c to the n. So now let's apply this to a real example and see where that gets us. So we want to find a fourth degree polynomial function f of x with real coefficients that has minus 2, 2, and I as zeros, and such that f of 3 is equal to minus 150. Well, the first thing we notice is that if I is a zero, then minus I has to also be a zero, the complex conjugate, because imaginary numbers always as zeros always come out as pairs. So if I is a zero, minus I has to also be a zero. So knowing the zeros of the polynomial, we can write it in general form as f of x is equal to a sub n times x plus 2 times x minus 2 times x minus I times x plus I, where the terms in parentheses represent the zeros or the roots. So if I FOIL some of these terms, I end up with f of x is equal to a sub n, x squared minus 4 times x squared plus 1. Now all that remains is simply to find out what a sub n is equal to. And here is where that additional bit of information which said f of 3 is equal to minus 150 comes in handy. I simply plug in 3 for x and let it equal minus 150 and solve to see what a sub n is equal to. So if we plug in x equals 3 in our polynomial and then solve for a sub n, we get a sub n equals minus 3. Now we can go back into our polynomial, plug in a sub n, and get the answer that we were originally looking for. So the answer we've got is f of x is equal to minus 3 times x squared minus 4 times x squared plus 1. So this is the fourth degree polynomial function that we were originally looking for and is the solution to our problem. Now I would like you to find all possible rational zeros for f of x is equal to x to the third plus 2x squared plus 6x minus 4, and then test to see which of these are actual zeros for this function. Post your answers in the drop box.